2, 1. Okay, so polynomial functions test. Here's a good one for you. So it has 5 questions, but there's multiple things to ask. And let's kind of get started on this one. I'm excited to try to go through this. If you want to download it, try it for yourself, just go into the show notes, click on the link, and then you can get the PDF file. If something goes wrong, put up a comment and I'll try to follow up with you. All right, so for this test, it's purely on polynomial functions. The assumption is that you're kind of in grade 11 and you're going through this and you want to try to see if you can test yourself. So I try to think of all the different items in polynomial functions by grade 11 that you should know. All right, so here's question 1. Given the following functions, so there's 2 of them, f of x and g of x, and we have a slew of questions asked about them. Okay, so let's try these first. I'm going to copy this down. Let's bring it, and I'll bring it down here so we can work on it. So the first part A states, what is the degree of each polynomial function? So that one, I guess, is a little bit easier. So for the degree or the order of a polynomial, so we're just looking at the highest degree of the terms that we have. So for the first one, so for this one right here, so this would be, I guess, of degree 4. And then for the second one, this is of degree 3. So that's part A. Now, second thing is, does a maximum or a minimum of the function exist? All right, so I guess let's take a look. Now, for these, so what do we know about maximum or minimums in polynomial functions? So there is actually a pattern, so you may kind of remember, or hopefully you remember if this was asked. Even ordered polynomials or even degree polynomials will always have a maximum or a minimum. And because they're kind of always going to be, I mean, there's going to be all kinds of junk maybe happening in the middle, but then they will stem up either upwards or downwards, kind of like quadratic. So those are even ones. So for the first one, we definitely have, and what would that be? I guess, so this would have been, we would have had a minimum. And the reason why it's a minimum, because the a of n, in this case a4, all right, is equal to 2, and it's positive. So if it's positive, that means this thing in the long term is going to be spinning upwards. Okay, it's going to be dominated in that way. So we do have a minimum there. For the second one, g of x, well, that one is of odd order. So odd order ones never have a maximum or minimums. I mean, unless there's some restrictions that they've put on the domain. But in this case, there are no restrictions. So these odd polynomials are going to go span upwards and downwards, okay, either this direction or that direction. So in this case, we do not have a maximum or minimum for g of x, but we do have, I guess, a minimum for the f of x. So that's the second one. Part C, find the domain and range of each function. So this one, I guess this will depend, you know, if your teachers do allow you to utilize some graphing tools or not. So I would kind of make the assumption that, you know, they might give you some hint or something like that. We're going to try to graph this out and then see what happens. And in grade 11, you know, until you kind of get into, you know, you understand a little bit of calculus and derivatives, I know that you know about slopes. But if you do know calculus and derivatives, this question actually wouldn't have been that bad. But because this is kind of grade 11, let's make the assumption that on this test, to find these domains and ranges, especially for f of x, because we do need to know what that minimum is for the domain. So we'll try to graph it. But here is kind of how I would go about it. So g of x is kind of simple. So because g of x is of odd order, and there are no restrictions at all, then it's pretty easy. So the domain, I'll just write d, okay, for the domain. So that would have been all of x, okay, and those are the entire real number. So x belongs to the real numbers because there's no restrictions at all, so nothing happens there. So that's great. And then for the range, okay, so the same thing. So the range for odd ones with no restrictions, okay, so the range you can, I guess, we'll call it g of x here, is also going to be the entire thing. Okay, so because at some point it's going to take on every value on that g of x, which is going to be your output. So that one is easy. The harder one is the even order ones, so that's f of x. So for f of x, because it's even order, so this is kind of funky. So we have, there are no restrictions ever on polynomials, and so for the domain. Okay, so that's the key thing, I guess, when you're studying, you know, you realize that polynomials are very nice to work with. Okay, so because there's no denominators, nothing crazy happening with these. So this one is, again, it's easy. And then for the range, so what you will have is, and so this is f of x. Okay, so that's the range. Sometimes people put y, so that just depends on your teacher. So it is all the real numbers such that, okay, so there will be a restriction because there is a minimum. And, okay, so where was this? This is to the 4, so there will be a minimum. So if you were stuck, let's say if this was a test and you weren't sure what to do, and you know you didn't want to keep plugging away in a table of values and just trying to see and narrow down that minimum. So what I suggest students do, and I would pretty much give you full marks if I was marking this, is if you do recognize that there is a minimum, and basically you say that f of x is going to be greater or equal to that minimum, okay? And then you just simply put whatever that minimum is. Now, of course, we would want to find what that minimum is if it's possible. But if you're running out of time, if you do this, then this is actually the correct answer, because there will be a minimum for that range, and then it will be just above everything that we have. Let's graph it. All right, so here it is. So it's graphed right there. So notice that there is actually a minimum. Okay, so the minimum is right there. So it's probably in some way approximated here by decimals. So I put this entire function in. So it happens at 1.21, okay, so around there, and the minimum is negative 1.238, all right? So give or take, that's what it would be. Okay, so that's our minimum, and that's what you could have put if you were allowed, let's say, to be able to use some kind of a graphing tools. Because ultimately, let's say what I'm interested in from students is, you know, do they understand the concepts? Because finding stuff in kind of real life, you know, we do utilize other tools. And so, you know, if you're in grade 11 and you weren't able to use these tools, most likely you would have been using some kind of a table of values, or maybe your teacher told you, you know, search within this range or something like that, that you can find it. All right, but that's the minimum. So it's negative 1.238. It's probably rounded. Okay, so don't forget that. All right, so let's just negative 1.238. Maybe it's rounded in some way. All right, so that would have been your minimum value, and notice that your range is everything above it. All right, so that's C. Now for D, find the zeros of each, I guess, of the polynomials. Okay, so this is another one. Now, if you want to find the zeros, you know, you can try to fool around and see if you can factor these polynomials out, right? Because that's what zeros are. So you can try to see, okay, let me take f of x, let me try to see if I can factor out, but it is to the 4th order, so that's actually kind of hard, unless you have some hints given to you. So that's one. And even to the 3rd order, the g of x, is also not exactly the easiest thing to try to do. So again, you know, if you were doing this, you know, you can kind of think about, okay, so how many, you know, zeros might we run into for this particular function? Let's do this by actual graphing. So I will assume, you know, that we're going to be doing this by graphing. Okay, so we're going to find those zeros. So zeros are the x crossings, right? Where that function crosses the x-axis. Those are actually the zeros. Well, we already plotted one of them. So if I bring this one back, so we have 2 zeros. So I guess we have one happening there and then one happening there. So there you go. So so we have 2 zeros, although it is to the 4th order. All right. Okay, so those are your zeros. So we've allocated them, and you can graph it, and then as long as you kind of identify what they are. If you weren't allowed to use a graph, and then what you can do is, okay, you can try to factor, but as you can see, these ones will be next to impossible to factor. Like I honestly, me looking at this, I'll be like, okay, I'm graphing this, right? I wouldn't even kind of play around unless it's a quadratic, right? But this is to the 4th order. So the other component that you can do is with the zeros is, you can start playing around with a table of values within a range. But if it's taking you too long on a test, just say what you would have done, okay, instead, in order to find it. So in this case, we would graph this one. Now the second one, the g of x, so let's plot that one as well. And so let's go back here and let's plot it. All right. G of x was 5x cubed minus 5x minus 4. Now, I do want to say something with the g of x. With the f of x, because it's even, it may or may not have 0 crossings. All right? Because that minimum could have been above, and then we would have never had any 0 crossings. But for odd order, you're guaranteed to have at least 1 because it's odd, okay? And it has a range which spans the entire thing. So you're guaranteed that it will have at least 1. It might have more. So here, well, the zeros that we have, so in this case, so this is, let me take the other one out, f of x. So this is g of x. So it looks kind of funky, but really there's only 1 crossing, and that crossing happens right there, 1.276. All right, okay, so that's what we would have, okay, within here. So those are your zeros. So there's only 1 actual crossings that we have, and we did it through graphing. Part E, find the nth difference of each polynomial. Okay, so we can certainly do that. And please don't use a table of values, okay, in terms of finding the nth difference. You should kind of remember. So for instance, so from this one, the nth difference is always a of n multiplied by n factorial, right? That's kind of the formula that we had. And you can check the videos, okay, within grade 11 that I posted on all of these polynomials, you'll see that. Okay, so on the nth difference. So what that means is, well, a of n is 2, and then n factorial, well, n is 4. So this is going to be 4 times 3 times 2 times 1, and there we go, and that's our answer, right? Okay, so we have, so 2 times 4, 8, 8 times 3 is 24, 48. Okay, that would have been the nth difference there. Then for your second one, so for this one, the nth difference, so now a of n is 5, and then it's 3 factorial, so it's going to be 3 times 2 times 1, so that's 15, so that's 30. So those are your answer for the nth difference of the polynomials. All right, so part F, find the point of intersection between f of x and g of x on the interval 0y. So this is, again, a very mean question. If you kind of had to do this by hand, so you would have had to say, okay, well, where do they intersect? And so you would have to equate the two functions and then try to find, where they actually intersect. In this particular case, so you would have to say 2x to the 4 minus 3x to the 3 minus x plus 1 equals 5x to the 3 minus 5x minus 4. And basically what you're doing is you're trying to solve this for x. That's very mean, right? If it's linear, then even if it's quadratic, those ones are much easier to work with. Here you can, move all the terms to the left-hand side. You can collect your like terms and then trying to see if you can factor it in some way so that you can get x. When it's this particular, unless you have some more information, certainly use the graph. Now they do give us a hint because they say between 0 and 2. So, technically, I guess you can move everything to the left, arrange everything, and then start plugging in, like by a table of values, values between 0 and 2, and then trying to see, where are you getting closer and closer to solving that equation, okay, when it equals 0. But we did plot this already, so we kind of have this. So notice between 0 and 2, so the intersection between these two, so that's the intersecting between blue and the red, and that happens right there. So that intersection happens at 1.207 approximately. So when you were doing a table of values, let's say, every 0.1, you would substitute it back in, okay, eventually you would see that like, somewhere along here, these two guys are actually equal. But plotting it, it's so much nicer because the idea is the intersection means is where the two functions actually cross each other, all right? And that happens, so it's between 0 and 2, so that's right there. Now, are there any other intersections? No. It does look like they intersect somewhere above here, but I think that's going to be much further. Yeah, it's going to be much further than 2. So there's only going to be one intersection here, and that intersection happens, right there in that spot, 1.207. If it's rounded, it's approximately that. All right, so that was another one. So this just really tests your understanding of all of these things, maximums, minimums, zeros, what do they mean, domain and ranges, and that's the point, right, of most things that we have. We want students to be comfortable in understanding the concepts, and then sometimes you can use technological tools like graphing to find these things, especially in grade 11. It's super neat, and I hope that your teachers allow you to use that. If you're in grade later on with some more math, you can use other tools that you have. Okay, the last one, find the local maximums or minimums of each function. So these are the local maximum and minimums. So let's take a look, okay, at the graph and then identify them. Are there any maximums or minimums, okay, within here? So let's do this one first. So this one looks like there is not really a local one. This is an absolute minimum that we have, and there is really no local ones that we have. I mean, here when I zoom in, as you're going along here, it looks like maybe there is some maximum, maybe it goes like peaks up, but it slows down, okay, changes kind of directions and goes in here, but there's really no zero, all right? So if you're noticing as you're going through here, okay, this is really the only minimum where it changes and it starts to go up. Along this path right here, it's just kind of coming down, coming down, coming down, okay, and it's always just coming down. So there's only an absolute minimum. There's no local ones. But for this one, there certainly are. So here is your local. So that's your peak. That's your local max, right, in that region, because then it goes up and then it comes back down. And then here, in this point right here, at 0.577, that is a minimum, a local minimum, which is negative 5.925. Again, probably rounded. But there is no absolute maximum or minimums because it is of odd order, so it's going to skyrocket upwards and downwards. Okay? So that's what we have within here. So this was a great question, actually, because it asks you almost pretty much everything you need to know within these polynomial functions. Okay, let's take a look at question 2. And for this question, this looks like it's going to be a little torture of a question. Okay, so this is all in factored form. when it's in factored form, we don't really need as much graphing. We can at least approximate things, and we should know how to do that. Okay, so let's see what they ask. What is the degree or order of the polynomial? So that's the same thing as before. Well, this factored is of order 2, this one is of order 1, and this one is of order 2. So the total, if we would expand this, okay, our leading term, our top leading term would have been this, which is to the 5. So what order is this? This is to the 5th order. That's how we can tell, and you can tell through the factors there. What are the zeros? Well, this one we don't need to graph because it's already in factored form. So we have a 0, so coming from here. So this is of order 2, and the 0 here is going to be at -3, and it's of 2nd order right there. All right, so that's going to be one of them. Then we have one coming from x plus 1. So this one is going to be x minus 1. This is only of 1st order. And then the last one, x minus 2. This is squared, so this is of 2nd order. This one's going to be at 2. So those are my zeros. So those are going to be the crossings that I run into. All right, and probably are going to be useful at some point. Okay, so part C. Find the nth difference. Well, the nth difference, okay, well, this is our leading term. If we would have expanded it out, we don't actually need all the other terms. So even if it's in factored form, it's actually simple to find the nth difference. All you want to know is your highest order. But your highest order would have been the multiplication of your, your terms that you have within here. And that's x to the 5, so that means, so for part C, so the nth order, which is the 5th order, the a of n, so remember again, so the formula is this, times n factorial, and n factorial, is n minus 1, n minus 2, until, you basically are multiplying these and bringing them down. So this a of n is 1 times, this is to the 5th, so 5 times 4, 20, 60, 120. All right, so that would have been your answer for the nth difference. Part C, okay, so sketch by hand. Woohoo. Okay, so this should be fun. So sketch by hand. Okay, so sketching, let's try it. I always do these and they're not straight, and that's because I'm kind of the way I'm sitting and the way that I'm writing these out. Okay, so maybe I should kind of do that. Let's straighten up a little bit. Okay, so this is my x and y. Okay, so x and y, or h of x. That's what I'm going to be plotting. Now I need my zeros. So 1 is at -3. Again, I'm just sketching here. -1. And then at 2. All right, so I know that those are going to be the 0 crossings. Okay, so how do I sketch these factored forms? And okay, so I have done this again, so you can check the grade 11 playlist for these, for sketching the factored form. So this is to the 5th order, and my a of n's so is positive. So what I know is, so within here, okay, so this is going to be blowing up in this direction, and then this is going to be blowing up in this direction. Why? Okay, so please remember that when the order is odd, they kind of replicate our cubic. Okay, so you have to be familiar with how the cubic is kind of sketched out, which is like this. And any higher orders, okay, so we don't necessarily know what's happening here in the middle, but we know that it's going to kind of follow the x to the 3. Okay, so it somehow is going to be skyrocketing. So this is to the 5th order, so it's going to skyrocket faster than to the 3. but it's still going to go up. And since they're asking for a sketch, you know, we know this one's going up, this one's going down. Now, what happens at the zeros? Okay, so first of all, so at the zeros tell us, okay, much more than just that it crosses there, because it might touch. So here, if you recall, this 0, so x plus 3, is squared. So what that means is around that crossing or that touching, so that at -3, it's going to replicate a parabola because it's of the second order, means it's replicating a quadratic. So here, so as it comes closer, it's going to kind of bounce off like this. Okay, so around that -3, you know, if we would zoom in here, it's kind of looking like a parabola. All right, so that's what's going to happen. So it's going to go like this and kind of bounce off that -3. It's going to touch it, okay, and then bounce off there. So we know that it's touching right there. Now, at -1, so at that crossing, that is only to the first order, which means first order means it's linear, it's a line. So it's going to cross through. So it's going to cross through as a line. And we know that it's going to be, so somehow this is going to go like this. We don't know how deep it goes. We can find out, you know, more or less, okay, if we start doing a table of values. But here it says it's a sketch. So it's going to now go here. And then around here, it's going to look like a line. So it's going to cross right through. And then at 2, so notice at 2, it's again of second order. So that means that this is going to kind of go somewhere like this. It's going to be coming up. It's going to have some local maximum. It's going to come down. And here it's going to touch this. And again, it's going to look like a parabola. So this is going to look something of that nature. Now, these peaks, I might be off. All right. So it might be a little bit to the left or to the right. Might be higher or lower. But I do know that it's going to look kind of something of this nature as a sketch. So I do know what's happening around each of these values. I do know what's happening in the long term with these. And then the rest I'm just kind of filling in. And if you want to fill it in a better way, if you have time on a test, you know, you can do a little bit of a table of values to see how far it goes, or how low. All right, that's a sketch. So identify the local maximum minimums if they exist. Well, we do have them. So here, so since it only says identify, so here they are. So they're going to be somewhere along there. So there's going to be, if you're kind of writing on a test, you can say there's going to be some local minimum somewhere between -3 and -1. And there's going to be some local maximum between -1 and 2. Okay, so there's only going to be those that you have within there. Now, the other maximum and minimums that you have are going to be actually at the 0 touchings. So here, there's another local maximum, so a peak. And then right here, we know that there is also a local minimum. These ones we're guaranteed to know. So I definitely know these because those are the touchings. And then these ones are kind of approximated. So yes, so we have 2 of each. So that's pretty neat to see. And then graph the polynomial. Okay, well, let's graph it. All right, so here it is. It's graphed. Okay, so our sketch was definitely close. So notice, so here's the -3, here's the -1, here's the 2, so those are your zeros. Notice around -3 looks like a parabola, right? So this is what I mean when it looks close to it. Looks like a parabola down. Okay, so that's what we had. Around -1, it just looks like a straight line going through it, because it was a first order. And then here, this again looks like a parabola bouncing off of the 2. And then the rest, you know, if you sketch it out, it kind of looks like skyrocketing up and down. All right, perfect. And here were your minimums. Okay, so we know we had one here. So that was your maximum at -3. we had another one here, we had another one here, and then we had another one there. So 1, 2, 3, 4. So 2 maxes and 2 minimums, local. There is no absolute maximum or minimum because they skyrocket up. So that was another question for you. Definitely one which tests your ability to understand these concepts. Let's take a look at question 3. Hopefully they get a little bit shorter. These things are bloody long. Whoever was doing this to you was mean, and the person is me, because I made the test. So that's what you have. All right, so the next one, so here's m of x, so another function. This one actually is a rational, so it's not exactly a polynomial. This is a rational polynomial, so we have a numerator and a denominator. Okay, what do they ask? First, what restrictions would have to be set on the domain? Okay, well, for rational, we do have to now have restrictions because we do not want to have the function kind of 0 over 0 or a number over 0. We don't want to have indeterminate or undefined results. So we have to restrict our denominator. So this thing we have to restrict. Now, luckily, this is just a quadratic, right? X squared minus 2. And in fact, it's difference of squares. So you should recall that difference of squares. So difference of squares, they have this form, right? And then so you can factor these out in this form like that. All right, where our y in this case is that I guess it's square root of 2. Okay. So for part A, in terms of restricting our domain, so we cannot have x. So here our restriction on the domain. So x, okay, is all real numbers, but it cannot be, and here, so you can do it one of two ways. You can say x squared minus 2. So this cannot be 0. So we have to find out where it's 0. And so that's simpler to do like this, right? Plus minus. Or you can use the difference of squares, which is going to be x minus that and x plus that. Okay, and both give you the same result. So that means x cannot be equal to plus or minus square root of 2. So those are the restrictions on the domain. So you're going to run into some undefined results there, or indeterminate. Part B, perform long division on the rational polynomial. Okay, long division. Oh my gosh. Okay, so let's do it. Okay, so x squared, we have no x terms, but I will put 0x plus 2. I don't know, I always like doing this. I just zero off all the terms that are not there. And next, so we have x to the 5 plus 3x to the 4 plus 0x to the 3. That's because there is no cubic term, minus 3x squared plus 0x plus 5. It's going to be long. Okay, that's all right. Okay, let's try it. Okay, so first of all, the long division. So notice that our numerator is of the 5th order and our denominator is of the 2nd order. So 5 minus 2 is 3rd order, right? Right there. So I'm going to start above there. So that means our result should have, okay, to the cubic. Okay, so let's do the long division here now. So this is going to be actually just x to the 3. So now x to the 3 times all of this junk. So that's going to give me x to the 5 plus 0x to the 4 plus 2x cubed. All right, so this is what I have here. So minus, so that cancels, and I have 3x to the 4 minus 2x to the 3. I'm going to bring this one down. Bringing it down because I need 3 terms, because this has 3 terms with that 0x. Okay, so now next, so what do I need? I need to cancel off this. So that's going to be a 3. So plus 3 and x to the 2. Okay, so that gives me 3x to the 4 plus 0 x to the 3 plus 6x squared. I mean, long division is annoying, but I mean, it certainly is possible. So, okay, that's gone. It's going to just leave me negative 2x cubed. This is going to leave me negative 9x squared. Okay, I can bring this down, plus 0x. And now again, so getting rid of this, so that's going to be negative 2x. And so I'm multiplying it by all of that. It's going to be negative 2x cubed plus 0x squared minus 4x. And so this is the last step now. So this is gone. So subtract minus 9x squared. And there's going to be plus 4x. And then bring down this 5. So that's going to be minus 9. So minus 9x squared plus 0x minus 9, so it's 18. Okay, subtract, and this just will leave me now the remainder. So this is gone. 4x, 5 is going to be plus 23. All right, so that's your result. So this is your quotient right here on top, and then this is your remainder that you would have. All right, so that's the long division process. They don't actually say anything else. They just say do the long division. So we did the long division. All right, so that was another one for you. And so luckily this one was shorter than the other ones. Here is question 4. Let me paste this back in here. So these are power functions. So they're polynomials, but they're nicer polynomials. They're power functions. And all power functions we know either cross through 0, 0, or they touch 0, 0. So these ones are much, much nicer. So sketch each power function, no problem. So in terms of sketching, so if I do my xy, so let's say like this. Okay, so the first one, f of x. So again, I always remember a quadratic, which is a parabola, as a power function, so meaning x squared. And I always remember cubic, which is x to the 3, and how they look like. So quadratics kind of look like this, that the parent function, okay, and then a cubic kind of looks like that. And then everything else is basically some kind of a transformation of that. Or a reflection. So this one, because it's negative 3, so that means instead of doing this, kind of like that, the negative 3 is going to reflect it because it's negative. So ours is going to look something like this. It's going to be like this, okay, and it's going to reflect back like that. It's going to have a faster rise in this case than the cubic. All right, so it's going to kind of push itself, you know, in this direction a little bit more than a cubic would. All right, and it's going to stretch down to 0 faster around here. But this is your f of x, so that's kind of how it's going to look like. All right, so let me remove this. So and again, it just says a sketch. And that is to try to teach you as a student to get kind of familiar with like, okay, how do these things kind of look like more or less? And then we can use tools if necessary. Now the second one, g of x, in this case, I'll use a different color. So it is to the 6th order, so it's even, and in front of it is a 2. So it's basically going to look like that, except it's going to be kind of really squeezed in here at the bottom, okay, and really pushing out right there. All right, so that's what we have. So that's the sketch of those two. And you can put them up on decimals just so that you can see it. Notice this one's to the 6, this one's to the 5. So the orange one is, as x gets bigger, both positive and the negative values as they kind of grow, that one will actually stretch closer faster than the x to the 5. So that's what we have. Now for part B, what is the maximum or minimum of each function? Well, so f of x doesn't have a maximum or minimum. So that's because it's to the 5th order. But the g of x, it does have, and this one will be at 0. Okay, so it will happen at 0. So this is a minimum of 0. Okay, for the g of x. That you don't need any kind of graphing tools. Okay, for power functions, graphing tools are more if you really want to be accurate. But for power functions, we should know how to graph them pretty simply. All right, so that's another example. And here's your last one, I hope. This is a kind of a brutal test. Okay, so question 5, copy. Let's see what else they want to know and ask us on. Last question. So we have another function right there. In this case, at least it's to the 3rd order, so hopefully that won't be bad. Now factor the polynomial. Oh my gosh. Hint. Okay, so the polynomial has a 0. Okay, so if we have this hint, okay, then that's amazing. Because what that is saying is that one of the factors is either this, that's the -2, or is this, which is the 1, or is this, which is the 4. So we know that that's going to be one of the factors. Now, which one, we don't know. So how can you do that? You can do it in kind of few different ways. One way is you can do long division, right? You can try to factor and then see if it goes into it, and then check if the remainder is 0, right? Or a simpler way is use the remainder theorem. The remainder theorem, when you're using that remainder theorem, all you do is you just substitute and try to see, okay, if the remainder that you want is going to be 0. And that's kind of also the factor theorem that you have. So let's take a look and see what happens. So if I substitute -2, so what am I going to get? Okay, within here, because if I substitute, it should give me the remainder. So now this doesn't mean that it's going to be quick in any way. I don't know. So what would this give me? So 6 is going to be negative. This is the cube, so it's 8. 8 times, so that's 48. 2, that's 4. 4 times 7, 28. Plus 2. Well, this definitely is not 0. Okay, we're looking for 0, so it can't be this. Okay, unless I've done something wrong, but I don't think so in terms of the arithmetic. Okay, let's try the 1. So 6. Oh my gosh, I hope it's this one, because this one's easy. So 6 minus 7 minus 1 plus 2. 6, 7, that's -1. Minus 1. Okay, good. It's this one. 0. Okay, so the remainder is 0 there. So that means that must be the 0. All right. Now on a test, you probably are going to be, you still want to check the 4, but here they say that it has a 0 at that. All right, so that's definitely one of them. Okay, perfect. So now that we know that this is the 0, and so what that means is that this will go into that. I guess I'm still going to have to do kind of long division here. The reason for that is because I want to see what the quotient was. So if I have, that's okay. At least we didn't have to do long division for all of them, especially for the, you know, the x plus 2. So, well, let's do that. And I am checking x minus 1. So let's do long division because I want to get the quotient, which is going to be a quadratic in this case. All right. Okay, so it's going to be 6x squared, I guess. So 6x cubed minus 6x squared. Oh, this one is so much nicer than the previous one. And so for that, so negative 7, so it's going to be negative x squared. Let's bring this down. Now to get rid of that, so minus x. That's that. So minus 2x plus 2. So minus 2. And we know that this will be 0. Okay, and indeed it's 0 because we know x minus 1 was a factor. So in factored form, so here's 1, 0. Now this is a quadratic, right? That's 6x squared minus x minus 2. Okay, so let's try to see if we can factor this out. So for quadratics, you can use the quadratic formula. Let's see what this gives me. So 6 times this, which is negative 12. Negative 12, and then when added together, I'm going to get negative 1. Negative 1. Am I missing something? Okay, my mind's going blank. So if it's going blank and it's a test, and then I just use the quadratic formula. So for the quadratic formula, so I will have, so negative b, which is going to be 1, plus minus, let's see, I mean maybe it's not factorable, but let's see. So we have that, so b squared, so that's going to be 1, minus 4ac, and that's that, divided by, and this is 2a, so that's 12. I think I screwed something up somewhere. Well, we'll see. Okay, so 4, 6, it's 24, it's 48. Oh, this is 49. Okay, I definitely missed something in the factoring. Okay, so that's going to be 7. So that's 1 plus minus 7 over 12. Okay, not really. I guess, yeah, I wouldn't have been able to do it in this way, okay, because I can see that these are going to be just some kind of fractions. So 1 minus 7 is minus, I guess, 6. And so minus 6 over 12. And then 1 plus is going to be 8 over 12. So this is really a half. And then this right here is, I guess, 2/3. So those are going to be my, okay, so I have kind of this. So I have x minus 1 over 2. And then x, so those are my factors. And then x minus 2 over 3. Okay? So this is what I have in there. So I did miss, I guess, something. So it was what, 2x plus 1. Oh, that's right. Oh my gosh. Okay, so right here, so if I'm going back here, so 6 times this is negative 12. And then, well, what two numbers? Well, the two numbers are basically 4 and 3, because 4 times 3 is 12. So you would have needed negative 4 and then plus 3. That's what you would have needed. So instead of doing all of this, okay, so here, let me just complete it. So it's going to be plus 4, minus 4x plus 3x minus 2. And that's, so I'm just doing decomposition. All right, so now grouping these two together, so I can take out a 2x, and that's going to leave me 3x minus 2. And then, so here, 3x minus 2, and there you have it. So you have 2x plus 1 and 3x minus 2, which indeed, okay, is going to have those as zeros. All right. Okay, and in here, so this would have been just 2x plus 1. All right, so that's, we should have just done it in this way. So those are our factors. Okay, so it says from the polynomial, so factor the polynomial, so now we have it factored. So the result is, so x minus 1, 2x plus 1, 3x minus 2. Okay, so that's what our result is. Those are our results. Part B, from the factored form, sketch the polynomial. Oh my gosh. Okay, so sketch the polynomial. So I have these zeros. So sketching it. So again, now it's, so this one was, so 6x cubed. So 6x cubed. All right. And so which ones do I have? So from here, so this is at plus 1. That's a 0 at plus 1. From here, this is minus 1 over 2, as we got. From here, this was 2 over 3. All right, so that's, let's say, negative 1 over 2. Here is, let's say, 2 over 3. And then close to that is just 1. And so it's positive, so 6x cubed. So again, so that means this thing is going to go kind of like this, skyrocket up because it's positive. This one's going to skyrocket down. So that's outside of those. Now what happens at each one of these? These are all first order. So that means they're kind of going to be like lines. So this one's going to cross through here. It's going to start coming back, cross through there, and then like a line through there. So it's going to be something of that nature. Again, those local maximum and minimums, the height of them, we can approximate, give or take, and exactly, what they have, but this just says a sketch. So that's how a sketch would look like. And so that's pretty neat. Part C, if you were to divide the polynomial by 3x plus 1, then what would be the remainder? Okay, so that's just the remainder theorem within here. And so for that, well, so we would have to put it back into the form. So 3x plus 1, so what would it have been? This is x equals to negative 1 over 3. So we would have to substitute negative 1 over 3 in here to find, using the remainder theorem, what that result would be. All right. Okay, so let me just check that for you. Okay, so there you have it. Hopefully I've done the arithmetic correctly, but that's what the remainder theorem would tell us. So we would just substitute that in and then find 4 over 3. All right. Okay, and that brings the end to this grueling test. Okay, so thanks for watching, and I hope that you found this useful and challenging. Okay, bye everybody.